All right, 9-2 day 1. Focus is going to be a specific type of sequence called an arithmetic. When you see it, it's probably going to look and feel kind of like a linear pattern, because that's pretty much what it is. 9-2, by the way, will be split up over 2 lessons. All right, we talked in the first section about the concept of a sequence, and then the concept of a series where you add terms as you go. The whole section, the focus will be arithmetic, first day sequence, second day series. All right, so we talked notation-wise. Right, that we've got a bunch of terms, right? That's referring to the first 4 terms. We saw formulas. We could talk about what we'd call the general term, like an expression that would refer to any term in the sequence. And most sequences can be thought of as infinite. It can go on forever and ever. All right, to be arithmetic, we have to have a number d such that this is true. If we were to take any 2 consecutive terms, like the second minus the first, that needs to be the same if we subtracted the third minus the second. That would be the same if we took the fourth minus the third, and so on and so forth. Okay? That number is called d, short for difference, which is short for common difference. If a sequence is arithmetic, it always has this value for d that can be identified. Now, I talked in the first lesson that when it comes to writing a formula, we need a few more tools available to do this, and we've got some pretty good options here for an arithmetic. Okay, we'll notice a pretty clear pattern here as we list out the terms. Okay, a sub 1 is just your first term. So a sub 2, we would get that if we took a sub 1 and we add d. To get the third term, we would add d not once, but twice. And if we wanted the fourth term, we would add d yet again. So just as a reminder here, this is a sub 2. There's a sub 3. There's a sub 4. And now as far as a formula goes, I think this is enough that you'll catch on to the pattern. If we wanted any term, we could start with a sub 1, but notice the pattern as to how many times you would add the common difference. If you look at all 3 of the next terms, you'll see the common difference was added 1 fewer times than the term that we were getting. If you wanted to get the second, it was added once. Third, d was added twice. Fourth, it was added 3 times. So that's why I'm putting it in terms of n minus 1. So that formula is really good to use, really slick for writing an arithmetic sequence, which we'll do on the next slide. I'll also show you here how to get it in terms of n. You can do d times n. The tricky part here is you need to then figure out c. C is defined to be a sub 1 minus d. This is probably best described as saying it's like your 0th term. So you have to go backwards from You have to go backwards from the first term that you were given, a sub 1, but if you know d, that you can do that, okay? On the first example, I'll show you both of these, and then I'll switch over to n minus 1. I think it's the easier way to write the sequence, so that's typically going to be the one that I'll use. All right, so that's our goal on these three, and you'll see all four of these total. These are what I think of as the nice case, because really the relevant information that we need to write the sequence is the first term and the common difference. Okay, worth reiterating at this point that all of these sequences are arithmetic. Okay, so it is, you know, if we didn't know, we'd have to check like the difference of consecutive terms to see if we have a value for d, but here we know we're going to find it because it's, you know, we're presuming that it is arithmetic. First term plus n minus 1 times 3. Okay? Now a couple different ways that you could do this. I'm going to show you both just on this one, and then I'm going to leave it as n times 1. If you put it in terms of n, you could have gone and said 3n minus 1. Okay? Notice how I took 3 away from 2 to get what we thought of as that 0th term. Another way you could have done this is if you distribute that 3, you would have 3n minus 3. Combine your like terms, and you'd have 3n minus 1. Okay? That's the only one I'm going to write it out as both. From here on out, I don't really care if you put the sequence defined in terms of n or n minus 1. For the rest of these, I'm going to stick with n minus 1, just because I think it's easier. First term, again, is 2 plus n minus 1. All I have to multiply n minus 1 by is the common difference. And just from looking at that sequence, it looks to be 7 is the number that's added each time. Both of those involve addition. It's important to note that, although I don't think I worked an example in here where it comes up, d can be negative, right? Which would be like you're subtracting the same number every time, and the terms of the sequence could get smaller. So here we throw in some fractions, and perhaps d is a little bit harder to see. Because the general term would be 1 plus n minus 1 times, we need something. Okay, don't forget that what we can always do is we could take consecutive terms and we could subtract them. So the first one I'm going to do is the second term, which is 5 over 4, and I'm going to subtract the first term, which is 1. However, I want to write 1 as 4 over 4, and we get 1/4. Okay? Now again, that would be sufficient to plug this in and say, all right, that d is a 4th, there's the rest of our formula. Because we know, based on the context of this lesson, that the sequence is arithmetic. Let's say we didn't. All I would do is go on and check. Let's do third term minus the second term. We saw in the definition that as long as we just take two consecutive terms and subtract them, whether it's the second minus the first or the third minus the second, we should get the same difference every time. Let's just adjust that to a denominator of 4, and sure enough, Okay, we get a fourth, but that might be something you need to look at if you've got a sequence and you might have a problem later on in the unit where you don't know if the pattern is arithmetic or not. That's the way to check, is go do like 2 or 3 to verify that you're getting the same difference every time. All right, so for the most part, those were nice cases. This would be the not nice case. So in all those others, they had 2 elements that this one doesn't. The first is that the first term was pretty easy to identify. And other than the last one, you could kind of just look at the sequence and see the common difference. But at the very least, you could figure out pretty quick because you had consecutive terms. Okay, we had the first term and we had consecutive terms. This one has neither of those. The problem tells us that for this particular sequence, we know 2 things. We know that the 4th term is 20, and we know that the 13th term is 65. Those 2 terms aren't in a row, and neither one is the first. Okay, here's how we'd handle this case. I'm still looking for the same thing, and this is why it ends up being, the not nice case, is to get the formula, we really need the first term and then the common difference. And in the 3 examples we did above, we could identify that really, really quickly. Okay? Here's what we have here. Let's start with the first one. If we're talking about the term in the sequence that's 65, that tells us nothing about the first term. It does tell us that n is 13, and we still don't know d. (20) is the 4th term, so I could put in 4 for n, and there we go. We could simplify that pretty easy. Okay, 12 and 3. We have 2 equations, 2 variables, and the trick here is going to be if we were to subtract these 2 equations, things work out very nicely. As 65 minus 20 is 45. A sub 1 minus a sub 1 is nothing. This is really, if we go back to chapter 7 and we solved 2 equations with 2 variables using elimination, that's essentially what we're doing. 12 minus 3 is 9. And of course, that's with the variable of d. Well, there we have it. 45 divided by 9 is 5. There's really the first thing we needed. The common difference is 5. Now from there, you could probably figure out pretty quickly what the first term is by working backwards from the 4th. I want to show you here what you would do if that was really tricky. I would go back up to this equation and then say 20 is the first term plus 3 times 5. Subtract 15 from both sides, and the first term is 5. That's absolutely coincidental that the first term and the common difference are the same thing. However, we are good to go. First term is 5 plus n minus 1, and d is 5. It's a little trickier case, but if we set up 2 equations with our arithmetic formula, you can basically use elimination and we can get our first term and the common difference.